Our next area of focus is going to be on energy. All right, so we've spent a lot of time dealing with forces and how forces affect motion and how, force, mass, and accelerator, all that stuff's equal. So we're gonna kind of shift gears a little bit. We're gonna focus on the energy that objects possess. All right, and so energy. This is really what we need to know. We need to know how the mass of an object. Some of this stuff is going to be pretty basic stuff that you should already know. Kinetic energy. Obviously, kinetic energy is an object moving. The energy of an object caused by its motion. All right, and we're going to have a couple formulas here. I know some of you are like, no, not more formulas. We are almost there, all right, to get rid of the formulas. So we're going to go over a couple of these formulas, and I'm going to explain each of these a little bit more in detail. Now, the other thing that, the other formula that we're going to go over, so the kinetic energy is half the mass times the velocity squared. The potential energy due to gravity. All right, so this is due to gravity. So once again, we're going to factor in the gravitational potential energy. This is when an object is above the Earth's surface is going to be mass times gravity times height. So the mass of the object. So once again, in potential energy, I mean, it has the potential to exert energy just because of its position above the Earth. Because if once that object falls, it's going to accelerate due to gravity, and so it's going to have some potential. And then the other formula that we're going to look at is work. Now, work is going to be characterized as a force that causes something to move. Okay, so work, energy is defined as the ability to do work. So in order to, if that's what energy is, we need to know what work is. Well, work is done when a force causes an object to move. So our formula for work, all right, is going to be W equals the force of an object times, and then this is delta x. Now that looks super confusing, but really all delta x is a change, because once again that triangle means change. A change, and if you think of x marks the spot, a change in position. All right, so if that x changes, that spot changes, an object has changed its position. So the force applied to an object multiplied by how much that object changed, that's how you solve for work. All right, so that's going to be our work formula. And what we're going to end up finding is that work is actually going to be equal to the kinetic energy. We're going to talk about work energy theorems. I don't want to get too much into that right now. But all this stuff is going to end up being equal through the law of conservation of mass. So these are really the three formulas that we're going to focus on. I will give you these on the test, but just like other stuff, you're going to have to know how to solve for different variables, knowing what you have. All right, so knowing the formulas is going to help somewhat, but knowing how to apply them is going to be much more beneficial. All right, and I'm going to try to go through this relatively quickly, so this isn't a 20-minute video, but there's all different types of energy. There's electrical energy, there's chemical energy. The chemical energy is energy stored in the food and the bonds between the atoms that hold energy, and so when you chew and you digest food, what you're doing is you're gaining energy and breaking down those bonds. The sun has radiant energy, there's thermal energy. There's all different types of energy. All right, and I like this analogy. I thought this was a good analogy to help us understand energy. All right, energy is there's a fixed amount of energy in the universe. All right, and basically all that's going to happen is it's just going to be continually changing forms. All right, you can't create energy, you can't destroy energy, but it's just going to change forms. So if you think of it like as the energy, all the energy in the world is $100. All right, you can go to the store, you can go to the bank, you can keep some in your wallet, you can have some in coins, and you can have one $100 bill, you could have $100 worth of pennies. But basically, no matter what, you got $100. So if I've got $100 in pennies, I've got $100 in quarters, I got $100 in ones, I've got 100. It doesn't matter the type that it takes, the style that it's in. If you've got $100, it's $100 no matter what. All right, whether you got 100 in pennies, one $100 bill, doesn't matter. It's the same. Energy's the same way. All right, so energy is just continually changing forms, but it's not being created or destroyed. All right, and that's called the law of conservation of energy. All right, the law of conservation of energy states that the energy, and this is going to be so huge. Understanding this is going to be so important. Energy cannot be created or destroyed. It just is converted into another type of energy. All right, and so understanding this is going to help us solve really complex, like math problems that could be really complex, but it's not going to be that hard because we're going to understand this law of conservation of energy. All right, and this is just going through examples, more examples of how energy can be transferred and traced from one object to another. Solar energy gets converted into chemical energy, chemical energy in a battery getting converted to electrical energy, which gets converted into sound energy. Food you eat gets converted into the chemical bond. The chemical energy from the food we eat gets converted into kinetic energy when we move, etc. All right, so the different types of energy. All right, so energy can change forms, and that I can't tell you how important that's going to be to understand. Energy is going to change from one form to another, all the different ways we talked about, and we'll even throw work in there a little bit. All right, so here's our first formula. So the kinetic energy is the energy of an object because of its motion. It depends on the mass and the velocity, but much more obviously is going to be the velocity, because you take half of the mass, but you're multiplying it by the velocity squared. All right, so when you take a sample problem here, you take half of the mass, so a car is moving at 20 meters per second, a mass of 1,500 kilograms. What is the car's kinetic energy? So you take half of that mass, and you're going to multiply by the velocity squared. So the speed is going to really have a drastic impact. The velocity at which an object's moving is going to have a drastic impact on the kinetic energy of an object. Because once again, it's energy because of its motion. It's energy because of its motion. Potential energy is energy that is stored in an object. All right, so kinetic energy is energy because of motion. Potential energy is energy that is stored in the object. All right, now there's all different types of potential energy. There's elastic potential energy. If you think of a rubber band, when it's stretched, it's not actually doing work, but it's stretched and it's ready. It's ready. If it snaps, you'll feel the work when it snaps. If somebody snaps a rubber band on your skin, you feel that the energy that it had. All right, so if it's stored energy, so if I stretch a rubber band, I'm storing that energy up, ready. So if it gets released, it can come back in and obviously create energy. And chemical potential energy, I already talked about that. That's energy stored in the bonds between food. And then the one that we're going to focus on mathematically, especially to solve, is gravitational potential. All right, this is when an object is above the Earth's surface. It has energy due to the fact that, once again, we've talked about this already, that all objects accelerate at 10 due to gravity. All right, and the way you figure this out, this is the formula, is mass times acceleration due to gravity times the height of the objects. You take the mass, you multiply it by 10, and you multiply it by the height. Remember, the g is always constant. The g is 10 meters per second squared. That's our gravitational constant. All right, so really all you're doing is you're multiplying the mass times the height. Now sometimes you'll see this where the potential energy equals the weight times the height, because remember, to figure out the weight is the force of gravity. All right, so it talks about it here. Weight is the force of gravity, which is mass times acceleration due to gravity. So the mass times 10 times the height. All right, so basically, I'm saying a lot of things here, but basically this is our formula. If you know the mass and you know the height, you know g is always 10, you can easily solve for it. All right, so here's a scenario where it says a coffee mug with a mass of 1 kilogram is on a 10-meter high counter. So we know our mass, so once again, I'm going to write this over here. Our mass equals 1 kilogram. We know our height equals 10 meters. All right, and so our formula then is mass times gravity times height. So we know all these variables. We know 1, we have the height is 10, the mass is 1, and once again, the g is absent, but we know that's always going to be 10. So it would be 1 times 10 times 10. It is going to be 100. And our energy, by the way, I didn't really sit to focus on this. Whenever we do energy in terms whenever we talk about energy in this class, it's always going to be measured in joules, which is a J, a capital J. Should have said that earlier. Trying to get through this. All right, and then I'll let you guys do that one. So if you know the mass and you know the height, you always know the G. The G is always 10. Once again, it's not written there. I won't write it there. All right, you'll have to know that the gravity, the acceleration due to gravity is always 10 meters per second squared. Kinetic energy. So here we go. So our kinetic energy, we know the mass of the object is 10 kilograms. It's moving at a velocity of 10 meters per second. So our formula for kinetic energy, once again, we're going to have to solve this stuff. These are pretty basic equations so far. Half the mass times the velocity squared. So I'm going to take half of 10, so I'm going to plug in my numbers. I'm going to take half of 10 and multiply that by 10 squared. All right. So if I did the order of operations or simply plugged it into the calculator, I'd have 10 squared. That's the first thing you do is 100. 10 times half is 5, so I'd have 100 times 5. 5. Oops, put that down here. 500 joules. Could put it up there too, I suppose. Right. And then I'll let you guys do that one. All right, so now here's the tricky stuff that I'm going to ask you. So if I say, like, I'll give you this problem here, like I'll give you a lot of problems like this where you're going to be like, what the heck, I have no idea how to solve this. Because it tells you the amount of energy in this system. All right, now when I say a system, I'm just talking about the scenarios that we're talking about here. So there's 100 joules of energy in this system, and we're going to ignore other factors that could come in, like friction and air resistance and all that stuff. So we're going to ignore everything else that would create, you know, other forms of energy. All right, and so if we have 100 joules at the top, all right, so we've got 100 joules at the top and we had 0 joules of kinetic energy there. All right, our total energy here is 100. All right, so if I say, what is the kinetic energy at point J, you might say, you know, on the test, like, he gave me the formulas, pretty simple. I know my kinetic energy is half the mass times the velocity squared. Wait a minute, I don't know the mass. Or wait, how fast is it going? I don't know how to do that. Because I will give you the mass. I'll say, hey, it's a 2-kilogram ball or something. What's the kinetic energy? I don't know the velocity. How can I solve this? So I'd have to really do some complex math to figure this out. Or you can just understand the law of conservation of energy. The kinetic energy, if the potential energy due to gravity, all right, because once again, the mass times the gravity times height, its potential is 100 joules. The kinetic energy is 0. Well, if I know that energy is not created or destroyed, when it rolls down this ramp, once again, we're ignoring friction, air resistance, all that stuff, or even if it fell down here, I know that once it rolls down, all of this potential, it has potential due to its position above the Earth's surface. Well, what's the potential energy down here? Well, it's not above the Earth's surface anymore, so its potential energy, the energy due to gravity, is 0. All right, well, where'd all that energy go? It can't just disappear. It had to go somewhere. Well, all that energy simply just converted into kinetic energy. So all that energy that it had up here, it didn't disappear. It's now 0 joules. It's simply just converted into kinetic energy. Okay, so they basically just changed form so that the 100 joules of potential energy as it rolled down that hill became 100 joules of kinetic energy right as it's hitting the bottom. All right, and so that's the kind of stuff that I'm going to ask you, and I'll ask you to solve for, eventually I'll ask you to solve for like the velocity and other things like that, but same thing here. So if the ball, just as it hits the ground, you might say, how would I be able to solve for any of this stuff? Well, the potential energy, it's pretty simple. If it was 100 up there, now the height is 0. It's mass times gravity times height. Mass times 10 times 0. It doesn't matter what it is. My potential energy is 0. So if I know my potential energy is 0, all of that must have converted into kinetic energy. So my kinetic energy at that point is 100. All right. Can an object have both potential and kinetic energy? Well, yeah. I mean, obviously, think of a football being thrown through the air. Yeah, I mean, it has both. It has kinetic energy because it's moving, and it has potential energy because it's above the Earth's surface. It has a potential to exert more energy. So any object that's in motion above the Earth's surface has both potential and kinetic energy, and that's called mechanical energy. All right, so mechanical energy is the total amount of potential and kinetic energy in the system. All right, so like down here we have low gravitational potential energy, EG is how I'm going to abbreviate that, energy due to gravity, and we have high kinetic energy because the ball just got hit off the bat. All right, probably a Cubs guy hitting a home run, Addison Russell, no big deal. And then up here, as the ball goes high, it has a high amount of gravitational potential, and the kinetic energy, all right, is starting to dip down a little. That's going to be at its lowest point. And then as it falls back down to Earth, the Earth in a home run defeating the Indians, the gravitational potential energy starts to go lower, but all that gravitational simply is just converting back into kinetic. So it goes from high kinetic to as the ball goes higher, that kinetic, because now it's fighting gravity. So it's fighting gravity as gravity's pushing down on it. The kinetic is turning back into potential, because now it's slowing down due to gravity, because gravity's pushing down on it, but it's got kinetic energy. And then as it reaches the top and it starts to fall back down, it's going to convert from potential to kinetic.